Hello everyone, this is the first of a series of videos dedicated to transition metals and coordination chemistry. During these videos we will be looking at some of the key characteristics of transition metals, including their magnetic properties, and we will spend a little bit of time on that. We will also be looking at some key concepts on coordination chemistry, what ligands are, types of ligands, what is a coordination number and what coordination numbers you can have, and also we'll spend some time looking at isomerism in the context of coordination compounds. We will also see how to name coordination compounds. And finally, we will spend some time studying crystal field theory, which allows us to understand the structure of coordination compounds and also predict the structure of metal complexes. As usual, the topic is divided in several videos to make it easier to follow. This is an image of the periodic table to help us locate the transition metals in the periodic table. We are looking at the D block, so this section of the periodic table, and many important metals are included in this group, and we will be discussing quite a few of them over the next few slides. In general, metals, including transition metals, are found in solid inorganic compounds, what we call minerals. Minerals are named by their common names, which does not reflect their chemical names. So, for example, you can spot here iron 3 oxide, or here mercury sulfide, and as you can see, they have common names that are widely used not only in society but also in chemistry books. Transition metals are widely represented in biological systems, and they have a hugely important role. They have a structural role, or sometimes a catalytic role, or sometimes both. The nature of the metal and the electronic structure of the metal and the coordination environment, the atoms surrounding that metal ion, determines its structure and function. And you have here three examples. For example, hemoglobin with the iron atom in the center. You've got the example of a metalloprotein, a zinc finger, a type of zinc finger, which has two zinc atoms in the structure. And finally, you have the example of a vitamin, in this case vitamin B12, that again has a metal ion, in this case cobalt in its structure. Some essential metals are transition metals, and you can see here there is a table with essential metals and particular recommended doses for all of them, and the effects that the deficiency in those metals can have in humans. And you can spot here in the table quite a few transition metals which are essential and we need in our diet. An excess of metals, including transition metals, can also be a problem, and essential elements can be toxic at high concentrations. We have here, for example, Wilson's disease, which is a rare genetic disease in which the body cannot process copper, so it accumulates in the body and causing detrimental effects. You've got here generic graph that represents in the x-axis the idea of the concentration of a particular element in diet, and in the y-axis the biological function. And there is an optimum level which is different for each metal, in which the concentration of the metal in the body is appropriate to perform its biological function. Below that optimum level, we look at a deficiency in a particular metal, and in higher concentrations we are looking at the metal having a toxic deleterious effect, and eventually both deficiency and lack of the metal or an excess of the metal can cause death. An interesting characteristic of the atomic radii of transition metals, which is that the second and third transition series elements have virtually the same bonding atomic radii, and therefore they have very similar chemical properties. They behave chemically in a very similar way. there are two competing forces when you're looking at the atomic radii, that when looking at atomic radii and the radius of an atom that will allow it to form bonds. On one hand, with higher atomic number, you have a higher number of protons in the nucleus, and you have more electrons in the electronic cloud. But in the case of the d block, in the case of the transition metals, those electrons are in the d orbital, and they are not as efficient as the s and p electrons to counteract that positive charge that you have in the nucleus. Therefore, you see an increase in the effective nuclear charge, which means that that nuclear charge, that positive charge, is stronger and is more able to attract the electrons in the electronic cloud, and that favors a decrease in the radius of the atom across the period. On the other hand, you have to look at the metallic bonding strength, and that increases until the middle of the period, because in the middle of the period you start having to fill in anti-bonding orbitals, d orbitals, but anti-bonding ones, which decreases that bonding strength. Transition metals tend to have more than one oxidation state, and some of them can have many oxidation states, especially in the center of the d block. Most will have +2 as oxidation state, and that's due to the loss of the s electrons. And quite a few others will have oxidation states higher than 2, and that will be due to the loss of the d electrons as well as the e electrons. We will see that many form color compounds, and we will spend a bit of time looking at how the different elements can form, have different colors. And in many cases, when they make compounds, though with the same element, with the same metal ions, you will see that the color is different. So we will also be looking into why those changes in color when the same metal is in a slightly different electronic environment. Transition metals have some interesting magnetic properties that we will be discussing in the next couple of slides. Electrons are charged particles and they are spinning. Therefore, electrons have a magnetic moment. You can think of an electron as a tiny bar magnet. If you have all the electrons in your substance paired up, then that substance is what we call diamagnetic. It has no net magnetic moment, and if you expose that substance to a magnetic field, it will not have any effect on it. Sometimes you have atoms that have unpaired electrons, unpaired spins, but they do not affect those unpaired spins do not affect each other. They are randomly arranged, and when you put the substance in the presence of a magnetic field, they will arrange with respect to the magnetic field. That's what we call a paramagnetic substance. So they have unpaired electrons, they have unpaired spins, but they do not affect each other. You can also have a ferromagnetic substance. A ferromagnetic substance are atoms that have an unpaired spin, which do influence each other. When you put out an external magnetic field, those tiny bar magnets, those magnetic moments, align parallel to each other and parallel to the magnetic field. And when you take away the magnetic field, the substance maintains that magnetic moment. That rearrangement of the spins is kept. So it becomes it has a permanent. It shows a permanent magnet, a permanent magnetic moment, and we call that a ferromagnetic substance. And transition metals, iron is the most famous one, but also cobalt and nickel show this ferromagnetic property. You can also have something called antiferromagnetism. In an antiferromagnetic substance, atoms have ampere spins on adjacent atoms that align in opposing directions, and they have the same strength. These magnetic fields have the same strength, so they cancel each other. And for example, chromium is an example of an antiferromagnetic metal. Then you can have something called ferrimagnetism. In ferrimagnetic substances, the atoms have ampere spins on adjacent atoms, and they also align in opposing directions, but they do not have the same strength, so they do not cancel each other. So you have a net magnetic effect. And there are some examples, for example, some iron oxides show that property, ferrimagnetism.